So in this last of 3 videos on thermodynamics, we're going to cover a very important thermodynamic variable, Gibbs free energy, delta G, and we'll also finish this video by going over a sample calculation. And so, as mentioned, free energy is a very important variable that gives us lots of information about the chemical system. So first, to kind of help define what free energy is, it is, in fact, the chemical potential within the system. Another way to phrase that, it is a measure of how much chemical energy can be used and converted into work. Work can be in lots of different forms. One form of work would be in terms of electrical work. So we know, say, in a battery, that chemical energy is converted to voltage or work to run some sort of motor or other device. Well, delta G helps us define how that chemical energy can be converted into a voltage. Delta G also is implicated in equilibrium, and delta G tells us where the equilibrium position is in a chemical reaction and lets us know when we are at equilibrium. We are at equilibrium when delta G, when the chemical potential goes to 0. And so what we can use from the delta G, not only the actual magnitude of the value, but also the sign convention. What I really want you to be able to know later on in future work that we do, we will use delta G values in later chapters when we talk about redox reactions and other processes. You should know that if the delta G is positive, that the reaction will not happen unless we use external energy to drive that reaction. We can reverse delta G and turn a positive into a negative, but we actually have to put energy into the system. But if the sign of delta G is negative, then that means that this reaction will happen. It will go forward. You know, a combustion reaction has a value of that's negative for delta G. If you put wood in a campfire and you light it, it spontaneously happens. If you put a battery into your calculator, the electricity runs spontaneously out of the batteries due to the reactions at the anode and the cathode. That reaction, that chemical reaction, has a value that's negative for delta G. And so we can relate delta G to the first and second laws of thermodynamics, where we can relate delta G with delta H and delta S. And so I want you to be able to use this equation because a lot of information is in the form of entropy and enthalpy, but from that you can calculate the free energy. And so again, we will do this and use this equation to predict whether delta G is negative or positive and whether or not a reaction will occur. So in this example, I want to use this equation of delta G equals delta H minus T delta S as a means to determine whether something is spontaneous or not. And we're going to do this qualitatively, just with sign convention. And we're going to look at these two terms. We have delta H by itself, and we have a negative T delta S over here. So when does water freeze spontaneously? We know that water doesn't freeze at all conditions. It doesn't freeze at room temperature if it's 70 degrees outside. When does it freeze? When does that reaction become spontaneous? We know that the delta H has a value for water, and in the case of freezing, the sign of that value is going to be negative because the system is losing heat. On the other term, we have delta S. If we're going from a liquid to a solid, the system is becoming less disordered, more organized, so the value of delta S is going to be negative. So this entire term here with T delta S, that term is going to be positive because we're going to take a negative of a negative term. So this term is positive. But if the reaction is actually going to be spontaneous, those two terms on the right-hand side need to give us a negative value. Therefore, T must be small to allow the negative delta H to be greater than the magnitude of the other term. Does that make sense? So temperature needs to be small, small, small. The temperature will drop, drop, drop until that positive term, the negative T delta S, becomes smaller than the negative delta H. It's at that point that water will spontaneously freeze. And we know that happens at 273 Kelvin. So that's kind of how this equation works. It does predict the spontaneity of a process and tells us when it will work, when a system will become spontaneous. We can do the same thing with melting of ice, where, excuse me, let's see, where is my cursor? I can't necessarily find my cursor, but we can follow again by saying if the reaction will be spontaneous, delta G needs to be negative. Ice melting is where a system is actually gaining heat, so delta H is positive. And melting is going from a solid to a liquid, so the system is becoming more disordered. So entropy is positive. So when does this actually become a spontaneous process? Well, the second term, the negative T delta S, that is the negative term here. Delta H is positive. So we need that negative term to become large enough to overcome the delta H that's positive. When does that happen? That happens at a temperature of 273 Kelvin. At that point, the second term is positive enough, or I should say negative enough, to overcome the delta H. And so these are the equations that we will be using to do some of the calculations in this class. Now, just to remind you, the information that we're covering on thermodynamics is background information for you. This is to help give you a foundation of understanding how energy moves and what laws dictate natural processes. So we'll practice a few of these calculations, and I know all of you have done this first reaction here in Chem 107 or General Chemistry, and we will do similar reactions, use similar equations with delta S and delta G. They work the same. We'll use values from tables in the back of the book or ones that I provide you to do these calculations. And last, we will incorporate entropy, enthalpy, and free energy to solve certain problems. So let's finish up this section by doing an example and using our new set of equations to determine different aspects of the following reaction. So the Romans, over 2,000 years ago, discovered that if they were to mine calcium carbonate, heat it up, that they could produce a substance, calcium oxide or quicklime, that could be used in cements and mortars to build buildings and other structures. And it's something that we still do today in cement plants. And it is actually a pretty major contributor to carbon emissions, about 5% of the total. And so for that reason, I thought it was a good example for this class. And so I'm going to use tabulated data. So this is all values from the appendix in a textbook. And so these values are for calcium carbonate, these values for calcium oxide, and these values for CO2. This way, I have the values here for entropy. They are in units of joules per mole K. And down here for delta H, for enthalpy in kilojoules per mole, I have these values. So when we do our calculations that combine entropy and enthalpy values, we have to just adjust the units so that they can be additive or cancel out. So just note that. These little knots up here, this is telling us that these values in the tables are under standard conditions, which mean they're at 25 degrees C and also 1 atmosphere. The F at the bottom, that's what this is down here. The F is meaning that they're entropy and enthalpy values of formation, formed from the elements. And so the first part of this problem is, using the tabulated data, let's calculate delta G. Well, we're not given delta G tabulated value. I give you delta S and delta H. So we use the equations on the previous slide. You've done these calculations before, and we can find delta H reaction and delta S reactions, which then we can put into this equation to solve for delta G for the reaction. And so in doing so, we do the sum of the products minus the sum of the reactants. So we have our products here. Let's see, delta H first. We have our products here minus, and then we have our reactant. So we put this through and we get 178.8 kilojoules. We do the same for delta S, products minus reactants, and we get a positive 161.6 joules per Kelvin. Where did the moles go in the units? Well, remember that we're also following the stoichiometry. There's 1 mole of this for every 1 mole of that for every 1 mole of that. I hope you will look in a general or introductory chemistry book and remind yourself of a little bit more about these sorts of calculations. But in fact, the coefficient here is in moles, and each of these is times by the coefficient, right? Every one of these is times by the coefficient. And so if there was a 2 in front of, say, the calcium carbonate, we would have a 2 right there. So mind the coefficients when you do these calculations. They also allow for the cancellation of the mole unit. So now we put these values into our equation, but again, this is in kilojoules, this is in joules. I've decided to convert my enthalpy into joules. Now I can add the two terms, and I get 130,600 joules, or now I'm going to convert back to clean up my answer. I get a positive 130.6 kilojoules for this reaction, and it is for 1 mole of reaction. So we have to ask ourselves, is this process spontaneous under standard conditions at 25 degrees C? And we see the sign, and so we would say no, this is not spontaneous. This reaction does not happen at room temperature, and we know that. We need to heat it up. But how hot do we need to get it? That would be really important information to calculate before actually doing such a reaction. By heating it more than what you need, in that way you're wasting energy. So the second part of this problem down here, part B, it asks, well, at what temperature will the decomposition of calcium carbonate become spontaneous? Well, we know that that would happen when delta G becomes a negative value. So we want this part of the equation to be less than 0. So when does that happen? So we set our values to be less than 0, and we find that that occurs at 1100 Kelvin. So we need to heat it up to 1100 Kelvin, and at that point we will begin to convert the calcium carbonate to calcium oxide. So that is how we use delta G. We can use it to predict whether a reaction will occur, will it be spontaneous, and at what conditions can we make a reaction spontaneous. So I do have this one last slide, and if you've had enough, you're more than welcome to leave the lecture video. But this kind of summarizes the relationship between enthalpy, entropy, and free energy. And again, this is more background information, and I will try to be brief. But what I have here are 3 plots which show how entropy, enthalpy, and free energy change over the course of a reaction. And so I'd first like to go over enthalpy, because enthalpy, as the reaction progresses, I should say, its change is linear. And that kind of makes sense. As I go from reactants to products, and in this case, I am portraying an exothermic reaction where the system is losing heat and delta H is negative. You can imagine that if the reaction goes halfway, I've released half of the heat. And that totally makes sense. And so it is kind of a linear function when you put it relative to the progress of a reaction. Entropy, however, doesn't follow that same trend. Here, I am showing a reaction that goes positive, has a delta S that's positive. More disorder is created. The products have more disorder, more entropy than do the reactants. So we're going to get a positive sign. But when it comes to entropy, the products aren't necessarily at the maximum value of entropy. The maximum value of entropy actually comes before you create the pure product. Here you have pure reactant, here you have pure products, but actually you get the maximum entropy when there is a mixture, and that mixture in our scenario would have the highest entropy closest to the products, but still a mixture. So because of that, we get a curvature in the change in entropy as we progress through the reaction. So now if we consider how entropy and entropy affect the free energy, it's H minus TS. Well, we can take the top plot and then subtract T times the middle plot for entropy, and we get a contour of a function for free energy versus the progress of a reaction. And so because of the curvature of entropy, we also get curvature in the free energy. And what we find is this negative slope, negative delta G. It's this part of the reaction that is spontaneous. As we fall down and go through this reaction, it is spontaneous until this point. This is where delta G is negative. This slope on this end, if we started, say, from the reverse reaction, well, this part of the reaction has a positive slope, positive delta G. It is non-spontaneous. And what we have right here at the very bottom, what they call Gibbs Valley, is where the change, the slope of the function is 0. This is equilibrium. So it's at this point where reactions will rest. This is where all the chemical potential has been exhausted, and this is where a reaction reaches equilibrium. And so again, our next topic will be equilibrium. It's related to free energy, and free energy is related to the enthalpy and entropy of a reaction. So it's all tied together, and that's why I felt it to be important to cover this topic. Remember, know your sign convention, be able to use the sets of equations that I gave you, and I think you will expand your knowledge of thermodynamics and be able to use it in your future studies.